All right. Good morning, everybody. So our intro slide today shows you an electrophilic aromatic substitution reaction that was actually run in my lab a couple of years ago now, but this is an acylation, right? So you might recognize this acid chloride here that just has this long alkyl chain on it, and aluminum chloride, which is the catalyst that we talked about in class. Like, this is like a textbook example, and this is an actual reaction run in my lab. And we got 93% yield of the product that we wanted. So this is one of those examples where the para substitution was much preferred over the ortho substitution. But I think it's kind of a cool example to show that, like, we actually do use the reactions that we talk about in this class. They're very, very useful to make a variety of things. I think we were making this for a polymerization, but yeah, anyway, cool things. We actually use the reactions that we talk about. Some quick announcements before we start. Homework 1 is due tonight at 11:59 p.m. Hopefully you've started it. You do have unlimited attempts at every question. So we've gotten some questions about that. So you need to submit the homework in order to then be able to go back and then try the ones that you missed. But you should be able to go back and continually try again. So you have unlimited attempts. After you submit, you can then go back and review the assignment if you so wish. I know a lot of people like to do this right before exams, for example. So there's two options there. You can either click on your score to see the actual assignment that you did, or you can click on this thing called review assignment. And if you do that, you will get slightly different questions, but on the same concepts. And so it's just another tool that you can use to review right before the exam, for example, or just to go back and refresh on a particular topic. However, I learned recently that if you do not turn in the assignment, you cannot go back to review it. And so, one of the homeworks is going to be dropped at the end of the semester. So if you decide not to do one of them, that can be fine and will not affect your grade, but you will then not be able to go back and review it. And so if you would like to use that as a resource for studying, make sure that you turn in every assignment just so that option is available to you. Okay. Please keep going to OLS. We had over 200 students go to OLS last week, so that's awesome. Thank you so much. Please keep doing that. And then we heard you about the OLS answer keys. And so yesterday, all the 2302 teaching team got together and discussed it. And we decided that we will compromise, and we're gonna post one of the two answer keys on Friday. So after all the OLS are done, one randomly selected answer key will be posted on Friday, so that you can check your answers for the entire thing, because we recognize that you don't always get through the entire OLS packet in a single hour. And so this will allow you to go through the entire packet. And because the two packets are very similar, hopefully you can then use the answers for one to figure out the answers for the other. But even if you can't, you're always welcome then to come to office hours to ask those questions, ask them on the discussion boards, etc. So that is our compromise there, is that we will post one of the two answer keys, but you will not know which one. So please still go to OLS. They are designed to be done kind of together and like actually working through like in groups and facilitated by a TA. So you will get more out of it if you go to OLS than you will if you just do them on your own. And so that is the compromise that we came to. Questions on that? Okay, great. So today, we are switching gears, finally. We've been doing electrophilic aromatic substitution for the entire semester so far. We are now not doing that. And so we are now doing nucleophilic aromatic substitution, which is sort of the opposite of that. So for today, our 2301 review topics is to review hybridization of carbon atoms. So you need to be able to differentiate between an sp3 and an sp2 carbon, for example. This is very, very important for the mechanism. Some things about SN1 and SN2 mechanisms are going to come back. So they will continue to come back throughout the semester. So if you have not reviewed those, I think that's a really good one to review. And then also just heterocyclic aromatic compounds. So not all aromatic compounds are benzene. So pyridine, for example, is this guy. That's going to come back in this lecture as well. So we have 5 learning objectives, but they're basically all about nucleophilic aromatic substitution. The 4 Ps, so we'll talk about what the reaction is and how it works, explaining how orthopara electron withdrawing substituents affect the rate, how the leaving group affects the rate, and then predicting and explaining the stability of the intermediate, and then comparing electrophilic aromatic substitution and nucleophilic aromatic substitution. Because these look very similar and they are opposite. So it's very, very important that we are separating them in our brains, okay? Let's just jump right in with our first learning objective. So the 4 Ps of substitution of electron deficient arene rings through nucleophilic aromatic substitution, or NAS. This is sections 13.19 and 13.20. Okay, so before we get into the mechanism, let's just look at the overall reaction. I often abbreviate reaction as RXN, just because it's easier to write. So in case you're confused by that, RXN means reaction. So in this reaction, we have our aromatic ring. But now we need a leaving group attached. So I'm going to put that leaving group at the top. And we need an electron withdrawing group. We'll talk about that in a second too. And we are going to react that arrow ring with some sort of nucleophile. That nucleophile will have a counter ion. So I'll just draw that here. So here's our nucleophile. Here is our counter cation. And overall, what is happening? We are substituting the leaving group for our nucleophile. Our electron withdrawing group is still there, and our counter ion gets paired with the leaving group. So this is our overall reaction. So a couple of things that I want to point out right at the very beginning. We are now reacting with a nucleophile. If we are reacting with a nucleophile, that means that our arrow ring is not the nucleophile, right? So this is opposite to EAS. So all of the reactions that we've been talking about before today, the arrow ring was the nucleophile, but that is not the case anymore. We are reacting with a nucleophile, therefore the ring must be the electrophile. So it's actually a carbon on our aromatic ring is the electrophile. And it's always going to be the carbon attached to the leaving group, right here. So that is our electrophilic site. So this is already opposite to EAS, okay? Opposite. The ring is the electrophile. We are reacting with a nucleophile. And the overall reaction is to substitute our leaving group, which is going to be a halogen of some sort. So fluorine, chlorine, bromine, iodine, right? Halogens. And we're substituting that leaving group with some sort of nucleophile. There are lots of examples of what that nucleophile could be. Sort of the classic example is a methoxide. Okay, so that's the overall reaction. We are substituting an aromatic ring with a nucleophile. Nucleophilic aromatic substitution. So oftentimes what we see students do when they see this reaction is they try to compare it to SN2. So this may look like an SN2 substitution, which happens in a single step. So let's remind ourselves of what SN2 looks like. So you could have like an alkyl chloride or something, right? We have our electrophile that reacts with a nucleophile. Nucleophile attacks electrophile, leaving group leaves. Single step, the overall transformation looks very similar, right? We've substituted a leaving group with a nucleophile. It looks really similar. However, these are not the same mechanisms because there is no SN2 or SN1 at sp2 hybridized carbons. So what does that mean? So remember, if we look at this electrophilic site right here, in this SN2 reaction, where we have an alkyl halide, that is an sp3 hybridized carbon, right? Because there are two hydrogens here that are implied. So two hydrogens plus this carbon plus leaving group. 4 bonds to different atoms makes it sp3. Whereas for this nucleophilic aromatic substitution, we have our leaving group here. We have our electron withdrawing group. Our electrophilic site is here. That electrophilic site is sp2 hybridized, right? Because we only have a leaving group and 2 carbons, right? This double bond here makes it sp2 hybridized. So what we see a lot is people trying to do SN2 reaction. Well, they'll take the nucleophile, they'll attack that electrophilic site, and then the leaving group just leaves. That cannot happen. Can't happen. Single step, that's an SN2 reaction. You cannot do an SN2 reaction and an sp2 hybridized carbon. Don't do this. Please don't do this. This is one of the biggest mistakes that we see, like the most common mistakes that we see on exams. Don't do this, okay? It's not an SN2 reaction. You cannot do an SN2 reaction at an sp2 hybridized carbon. I'm gonna say it again. You cannot do an SN2 reaction and an sp2 hybridized carbon. Don't do it, never, cannot, okay? It cannot be a single step, it must be 2 steps, all right? So what is it instead? Instead, it's going to be an addition elimination mechanism, which is a 2-step mechanism. Okay, so SN2 is 1 step, addition elimination is 2 steps. So we're going to do it in 2 steps. So let's start with that same kind of generic leaving group. We'll talk about what that is in a second. And I'm going to draw it with a nitro group because the nitro group is by far the most common electron withdrawing group used for this reaction. Make sure that you feel comfortable drawing the nitro group out. It's kind of a weird one because even though it's overall neutral, there are actually charges. The oxygen that has 3 lone pairs is negatively charged. That nitrogen is positively charged. So this is the most common electron withdrawing group for NAS. Okay, so first step of our mechanism, we have our nucleophile. Nucleophile attacks electrophile, break the weakest bond, which is the pi bond. I'm going to put that on the closest carbon for now. Okay, so what did I do? I have my leaving group and my nucleophile attached to the same carbon. We've still got our electron withdrawing group down here. And I dumped electron density onto this ortho position, which makes it negatively charged. So this is our addition step, because we have added the nucleophile to the electrophile. So we've done the addition. So the reason that our electron withdrawing group is necessary is because it is able to stabilize that negative charge. So I'm not going to draw every single resonance structure, but I'm going to draw the most important one. So I'm going to move this lone pair to form a double bond on the left side, and then I'm going to shift this double bond over one, and we're going to push this electron density into the oxygen. So I would recommend drawing out every single step to make sure that you feel comfortable with those resonance structures. But for now, I'm just going to show the most relevant one. What didn't change, our leaving group and our nucleophile are still attached to the same carbon. Now, our nitrogen is double bonded to the ring. And we have two negatively charged oxygens attached here. Okay, and this whole thing has this counter cation. Okay, so the electron withdrawing group stabilizes that anionic intermediate via resonance, right? You can see how we've pulled the negative charge out of the ring or off of the carbon into this electron withdrawing group to put that negative charge on oxygen. Remember, oxygen, electronegative atom, much happier sitting with a negative charge on it. So the fact that we can put negative charge on oxygen, very good, much more stable. And in fact, this is actually necessary to make the reaction go in the correct position. We'll get to that in a second. If you do not have this type of stabilization, this reaction does not happen. Okay, very, very important. So that's our addition step. So we have a bunch of resonance structures for this anionic intermediate. Now we have to do the second step. So this is our elimination step. Okay, so our elimination means our leaving group has to leave. So we're just going to basically push all of our electron density back, starting from that negatively charged oxygen. We just keep pushing these double bonds over until we can make the leaving group leave. So again, you could draw every single resonance structure on your way back, but we often don't, because it just pushes all that electron density back up. Now our nucleophile is the one that's still attached to the ring. Our nitro group is back to how it was when we first started the reaction. So overall neutral, though it still has charges. And our byproduct is this counter ion with our leaving group. Okay. So let's just talk through that one more time. Two-step mechanism. First, we add. So our nucleophile adds. Because we're pushing electron density into the ring, it becomes anionic. The most relevant resonance structure is when we push that negative charge into our electron withdrawing group, which is our nitro group down here. Right? So now we have a stabilized anionic intermediate or negatively charged intermediate. And then in our second step, the elimination step, we push all that electron density back, leaving group leaves. Okay? Questions on that basic mechanism? Yes.
Why can't this happen in one step?
Because the orbitals don't line up to be able to allow the leaving group to leave at the same time that the nucleophile attacks. It's a little bit beyond the scope of this class, but it's because of the hybridization of that carbon. Because of the way that bonds are made, the alignments don't line up. Yes. Yeah, that's a good question. So yeah, so it depends on the question, how many resonance structures you have to draw. Usually, no. Most of the time, you can just draw one, which I'll give you an example of in a little bit later. But if we ask you, draw all of the resonance structures of this intermediate, then you would have to draw them all. Otherwise, you only need to draw one. Yeah, good question. Yes. Great question. This goes to the next slide. So the position of the nitro group matters. So this one's para, right? Let's look at the other positions to see if it works. Let's look at the other intermediates. Okay, so let's do ortho. So I will just draw the first intermediate, right? If I just were to dump that electron density on the adjacent carbon, we've got our nucleophile. I'm going to put that nitro group over here now. Okay, so this is our ortho intermediate. Now we're going to check, can I delocalize that negative charge into the nitro group? So again, there's a bunch of resonance structures here. I'm not going to draw them all, but this lone pair can push down to form a double bond. We can push this double bond over. We can push this double bond over. We can push this double bond up. So yes, this one works because there is a resonance structure where I can push the electron density up into the oxygen. So ortho also works. Let's look at meta. I put my leaving group and my nucleophile. I'm going to put my nitro group meta to the leaving group. So down here. Okay, so this is our meta example. So this is what the intermediate would look like. So again, I'm going to try to push that negative charge into the nitro group. So the lone pair can form a double bond here, can push this over, can push this over. It's not possible. I actually cannot push that negative charge into the electron withdrawing group. So this one does not work. So we can't delocalize the negative charge into the nitro group. So that means that if your nitro group is meta, there is no reaction because you can't stabilize that intermediate. Therefore, it's not going to happen. So that means that you need at least one of these electron withdrawing groups must be ortho or para to your leaving group. At least one ortho or para, because it needs to stabilize that negative charge. Okay. Okay, so that's the basic mechanism. Now we're just going to talk about variants of this and how different aspects of the aromatic ring affect this reaction. So our next learning objective is 13B. Explain how ortho-para electron withdrawing groups affect the rate of NAS. Okay. So what we've been talking about has been, for example, we have our halogen leaving group, so like a chlorine. We have one nitro group, right? So we talked about that. This one works. We can do it. And we talked about how if you only have the leaving group, but no nitro group, this does not do NAS. Okay, those are the first 2 points on a pattern. No nitro group doesn't happen. One nitro group does happen. Now I want you to think about what will happen if we have 2 nitro groups. This is our chime-in question for today. Not going to tell you the answer before I make you think about it. So now we are comparing one nitro group in the para position versus 2 nitro groups, one in the para, one in the ortho. Which one will undergo NAS faster? Okay, so again, you can chat with your neighbors, see if you can figure it out, and then we'll go through it together. Maybe 10 more seconds, get your answers in. All right, let's see what we got. Okay, so most people are getting correct, but we're not super confident, right? So A or B, not quite sure. So B is the correct answer. It's going to be faster because we have more electron withdrawing groups to be able to stabilize that negative charge. So in the same way that adding one nitro group is good, adding a second nitro group is even better. And so that allows us to do the reaction even faster. So let's draw that out. Okay, so we talked about how the rate of one nitro group makes it faster. So now, if we have two nitro groups, this is going to be even faster. And if we were to have three nitro groups, that would go even faster, right? So it's an additive effect because we're trying to stabilize a negative charge. And so anytime that you can stabilize it better, it's going to go a lot faster. So let's look at this again. So here we have our generic leaving group. We have our generic electron withdrawing group. So remember that this aryl ring contains the electrophile. Right? So I get why this question is hard for people because it's so opposite. Everything that we've been talking about for the whole semester has been nitro groups are deactivating, right? But this is different because the mechanism is different. So in NAS, our aryl ring is the electrophile. Remember that electrophiles are electron deficient, right? They are accepting electrons. So that electron withdrawing group makes our electrophile more electrophilic, right? It makes the electrophile more electron deficient, thus it is better at its job. If you make an electrophile better at its job, the rate goes up. So this is opposite to EAS, where the ring was a nucleophile and electron withdrawing groups made it worse at its job. Now, electron withdrawing groups are making it better at its job. So this is why understanding the mechanism of the reaction should be able to help you rationalize why these trends happen the way that they do. Questions on that? Yes. Yeah. Yeah, good question. So if you have one that's para, that allows the reaction to happen, right? And then one that's meta, so that will still be slightly withdrawing, but inductively, right? Just through the bonds and not resonantly. So it probably would be a little bit faster, but not a lot faster. Yeah, because inductively withdrawing is still withdrawing, just not as strong as a resonantly withdrawing. Yeah, good question. Other questions? Okay, so that's the leaving, or sorry, that's the electron withdrawing group and the positions and how that matters. Now let's talk about the leaving group. So our next learning objective is 13W. Explain how the leaving group affects the rate of NAS. All right, So this is also a little bit confusing because it is the opposite to the leaving group trends that you have learned previously. So leaving group trends are opposite to SN1 and SN2 reactions, which you've previously learned. So for SN1 and SN2, you learned that iodine is the best leaving group, then bromine, then chlorine, then fluorine. For NAS, it is exactly opposite. Fluorine is better than chlorine, is better than bromine, is better than iodine. So why is that? Again, for NAS, let's look at what that intermediate looks like. So again, I'll just draw this particular resonance structure with fluorine, whatever our nucleophile is, whatever our electron withdrawing group is. Okay, so remember, fluorine is the most electronegative atom, right? It is very inductively withdrawing. It's pulling electron density towards itself. So that means that it's going to have a stronger inductive effect because it is more electronegative. So that means that it is better at charge stabilization, specifically anionic charge stabilization, which then means that our rate goes up. So everything about NAS is about stabilizing the anionic intermediate. The better you stabilize the anionic intermediate, the faster it goes. Straight up. That's always true. So, but it's opposite for EAS. So that's why you have to like really understand which reaction you're talking about to be able to rationalize it correctly. Okay, so the more electronegative atoms just inductively stabilize that negative charge slightly better, makes the rate go faster. Okay, so that's sort of like the different parts of the reaction. So let's see an example, a full example of how I might ask for a mechanism on an exam. So the classic NAS reaction is with a fluorine leaving group with a nitro electron withdrawing group and with sodium methoxide as our nucleophile. This is like the most classic NAS reaction you could possibly do. Okay, so if we were to ask you to draw the mechanism of this reaction, generally, you would not need to draw all of the resonance structures. So instead, it is best to draw the best resonance structure, the most relevant resonance structure. So what does that mean? That means that when I do my addition step, so again, this cannot be in one step. So my first step is the addition step. My nucleophile attacks my electrophile, and then I'm just going to push all my electrons down one bond at a time until I push the negative charge onto the oxygen. So this is how we normally draw this mechanism because it shows you why that electron withdrawing group is necessary. So that puts the negative charge on the oxygens. Now we have two negatively charged oxygens in the nitro group, positive charge on the nitrogen there. We have our sodium counter ion. So this is the intermediate that is most correct because it is the one that's showing why the nitro group is necessary. Okay, so that's our addition step. If it's helpful for you to draw first that first resonance structure where you dump this electron density on this carbon and then draw it, that's totally fine. Just practice drawing the resonance structure so that you can see why those are the same structure. Okay, so that's the addition step. Now we do the elimination step. So again, we start from the lone pair on oxygen, we push the electron density back up, re-aromatize the ring, leaving group leaves. So that leaves our methoxy group on the ring. Our sodium fluoride is our byproduct, and our nitro group is back to how it was at the beginning of the reaction, which is overall neutral, but it still has formal charges. Do not forget the formal charges on the nitro group. Yes?
On an exam, would you get points taken off for different intermediate?
Depends on the wording of the question. If we ask you for like the most stable resonance structure, you have to draw this one. If we do not say that, then you can draw any of them. Yes. Okay. So that's the overall reaction. That's the overall mechanism. The next learning objective is essentially just being able to rationalize everything we've already been talking about. But again, it was like important enough to call out separately. So we made a separate learning objective for it. So this is 13x. So predict and explain the stability of the anionic intermediate in NAS using electronic arguments. So that's essentially what we've been talking about, right? Resonance structures are electronic arguments. And so it's just trying to connect the dots a little bit, that having a more electron deficient ring means that you have a more stable anionic intermediate. So as part of this learning objective, you should be able to draw the resonance structures to show why having a more electron deficient ring leads to a more stable intermediate. So being able to rationalize why having two electron withdrawing groups in the ortho pair positions are going to make a more stable adduct. So in the same way that it leads to a faster rate, it also makes a more stable intermediate compared to a single electron withdrawing group. So I know that that's a little bit repetitive. It's meant to be repetitive because we're trying to connect the dots between these different concepts. So not only does that second electron withdrawing group make the rate faster, it also makes the intermediate more stable. And those two things are 100% connected. Because the intermediate is more stable, it is also faster. But that's the kind of the difference between those two learning objectives. But the reason that this learning objective says electronic arguments and not just resonance is because it's not always resonance. So everything we've been talking about has been resonance. But now let me show you an example where it's not resonance. And you should also be able to rationalize why this works. So if instead of a nitro group, we have 6 fluorines, so hexafluorobenzene, 6 fluorines on benzene. We replaced every hydrogen with a fluorine. This is hexafluorobenzene. Those fluorine atoms are not resonantly stabilizing, but they are the most electronegative atom. So that means that we just put a lot of different electron withdrawing groups on it. So lots of electron withdrawing groups. And by adding that many different electron withdrawing groups, it stabilizes the anionic intermediate enough to make this reaction go. So if we were to use, again, that sodium methoxide, like the classic example, our nucleophile can attack our electrophile, break the weakest bond, which is the pi bond. This is our addition step. Now, there are different resonance structures, but they're not super relevant because none of them can put the electron density onto the electronegative atom. These are all inductively withdrawing. We have our counter ion, and I put the lone pair over here. So that's our negative charge. So that's just stabilized because there's a bunch of electron withdrawing groups on it. And it's inductively pulling that electron density away. So it allows this anion to be formed. And then we can do our second step, which is our elimination step, to push off the leaving group. So overall, reaction is still the same. We have substituted one of the fluorines for our nucleophile, made our sodium fluoride byproduct. But the rationalization for why this happens is slightly different than the other ones, because it does not have that resonantly withdrawing, it is inductively withdrawing. Okay, there's one other major example that works that you need to be able to rationalize, and that is where this heteroaromatic rings come in. So this is where pyridine comes in. So here's our pyridine. So this is also an aromatic compound. We just replaced one of the CHs with a nitrogen. And I'm going to put my leaving group, my fluorine, next to the nitrogen, the 2 position. So this is called 2-fluoropyridine. Okay. So if I were to do this NAS reaction with sodium methoxide, our electrophile is still the carbon attached to the leaving group. Always, always. Nucleophile attacks electrophile, break the weakest bond. Still the pi bond. This is our addition step. Let's look at what the intermediate looks like. So we still have our leaving group, our fluorine, and our nucleophile, our methoxy, attached to the same carbon. Still got our counter ion. Now our negative charge is on nitrogen, right? So I push that electron density onto the nitrogen. So that works because nitrogen is more electronegative than carbon. So that means that it's okay having the negative charge. So in this case, because we're putting the negative charge on an electronegative atom, it is happier with that negative charge. Therefore, this intermediate is stabilized. So that's the difference with pyridine as opposed to benzene. Okay, so we don't need additional electron withdrawing groups on a pyridine because that nitrogen is already being able to hold that negative charge. Okay, so that's our addition step. Again, we're going to have an elimination step where that lone pair pushes back and our leaving group leaves. So the overall reaction is the same. We have replaced our leaving group with our nucleophile. We have generated our sodium fluoride. It's just pyridine now, doesn't need an additional electron withdrawing group. Okay, so this is where the fluorine is in the 2 position. This also works if the fluorine is in the 4 position. So this is my challenge to you, is to draw the intermediate for 4-fluoropyridine. So that is when the fluorine is back here. Okay, so I will include the answer to this challenge in my notes when I post it later today. But that is my challenge to you, is can you use this information to draw the mechanism and rationalize why this intermediate is also stable for 4-fluoropyridine? Questions? Yeah. It's a salt. Yeah, they're ionically solvated in some way. We don't usually worry too much about the inorganic byproducts because you just wash them out with water. Okay, so in the last few minutes, our last learning objective is comparing and contrasting EAS and NAS, mostly contrasting, let's be honest. So learning objective 13Y, so we are going to compare and contrast EAS and NAS, because they are basically opposites, but I understand that they look very similar. Okay, so we're going to do a little bit of a chart I'm a big fan of charts to like organize all the information. So we're going to have EAS on the top. We're going to have NAS on the bottom. Okay, we're going to compare all sorts of things. So first, the role of the aryl. So the aryl is, in the EAS reactions, the aryl is the nucleophile, because it's being substituted with an electrophile. That's where the name comes from, right? EAS, it's being substituted with an electrophile. Therefore, the ring itself must be a nucleophile. For NAS, it's the opposite. The aryl ring is the electrophile, because it's being substituted with a nucleophile. Again, that's where the name comes from. NAS, substituted with a nucleophile. Therefore, the ring must be the electrophile. Okay. Next one. Is there a leaving group on our aryl ring? For EAS, no, we do not have a leaving group on the ring, because we are replacing an H plus, right? We're substituting a hydrogen with our electrophile. But for NAS, yes, we do have a leaving group. So yes, it's going to be a halogen. Fluorine is better than chlorine, better than bromine, better than iodine. Okay. Next one, do you need to use a catalyst? In EAS, often yes, right? So we talked about how, because the aryl ring is not a great nucleophile, you need to make a strong electrophile. So that you usually use a catalyst to make a strong electrophile to make EAS go. Whereas for NAS, normally no. So this is a very rare occurrence, and we're not covering it in this class. So it's not never, but usually no. For the purposes of this class, you do not use a catalyst for NAS. Okay? That's another big difference. Next one, what is the intermediate of the reaction? In EAS, the ring is the nucleophile. The ring loses some electron density as it reaches out to react with the electrophile. That makes the intermediate positively charged. It's losing some of its electron density as it's reacting with the electrophile. Whereas in NAS, the nucleophile is giving some of its electron density to the ring, so our intermediate is negatively charged. And it is an electron withdrawing group stabilized intermediate. And then we have our substituent effects. So for EAS, we spent 2 full lectures talking about how electron donating groups make the rate go up, and electron withdrawing groups make the rate go down, right? That's the activator, deactivator language. And again, relate that back to the fact that the aryl ring is the nucleophile. So if you have an electron donating group, you make the nucleophile better at its job, it goes faster. Electron withdrawing group makes a nucleophile worse at its job, it goes slower. NAS is now the opposite. If we have these electron withdrawing groups, it makes the rate go up. And there's no reaction if there are no electron withdrawing groups in those ortho-para positions. Again, that relates back to the fact that the ring is now the electrophile. So making the electrophile more deficient makes it better at its job. The rate goes up. Okay? So hopefully this chart is helpful. I know that these are really confusing because they look really similar, but they're exactly opposite. So it's super important that you can divide them in your brain and don't get them mixed up. Okay? So that finishes chapter 13. On Friday, we'll start chapter 15 in organometallics. Thank you very much.